Good morning, everyone. This is Teacher Eda Montano, and today we will be talking about the condition number of a matrix under the numerical linear algebra topic. Okay, let's start. So, what is the condition number of a matrix? Let's find out. Now, for us to be able to understand this specific topic, we have to take note of the following words, which are very important. The matrix norm, the condition number, singular matrix, non-singular matrix, ill-conditioned problem, and well-conditioned problem. And every word will be discussed in their respective slides. Okay. For the condition number of a matrix, a condition number for a matrix measures how sensitive the answer is to perturbations in the input data and to round off errors made during the solution process. Now, if we talk also about perturbation, it's the set of mathematical methods often used to obtain approximate solutions to equations for which no exact solution is possible, feasible, or known. Okay, let me just use highlight a laser point, okay, to give emphasis to our discussion. Now let's move on to the next slide. In the field of numerical analysis, on the other hand, the condition number of a function measures how sensitive a function is to changes in error in the input and how much error in the output results from an error in the input. There are many different condition numbers. In general, a condition number applies not only to a particular matrix, but also to the problem being solved. Are we solving linear equations, inverting a matrix, finding its eigenvalues, or computing the exponential? A matrix can be poorly conditioned for inversion, while the eigenvalue problem is well conditioned, or vice versa. However, when we simply say a matrix is ill-conditioned, we are usually just thinking of the sensitivity of its inverse. That is, of the condition number for inversion, and not of all the other condition numbers. So here in this topic, we will just focus on the basic discussion of the condition number of a matrix. The condition number of a square non-singular matrix is defined by the given formula. And this formula is read as, okay, let me just use another laser point. Okay, this given formula is read as the condition number of A is the product of the norm of A and the norm of A inverse. And later on also, I'll be teaching you how to get the matrix norm. Okay, we will be using this formula in solution and in identifying if our given problem is an ill-conditioned or a well-conditioned one. Okay, now by convention, the condition of a matrix A is infinite if A is singular. And how do we know that our given matrix is singular? Now, we have to take note of the given definition, statement rather. If a matrix does not have an inverse, the matrix is said to be singular. On the other hand, if the matrix have an inverse and that matrix is called non-singular matrix, also known as regular matrix. Okay? Sige. Now, later on, we will also use this formula. Let me just use a pin. Okay, because the condition number depends on the matrix norm that we will be using. Now, given the condition A, okay, condition of the matrix A is equal to the norm of A, then infinity. This will be our subscript. Okay, in our example, we will still be using this. And we have A inverse, the norm of A inverse, infinity. Okay? Okay. Now let's move on to the next slide. To illustrate further the condition number of a matrix, let's consider the given equation. Okay, let me just use a pen for a while. Let me click this one. Okay, now let's consider the given equation. Ax is equal to b. And suppose b has some error. Okay, b has some error. Then when we solve the equation, we will not get x, but instead, we will get a value near x. Okay? Now, in this particular example, the condition number is a relative error magnification factor. Let me write relative error magnification factor. Because the changes in the right hand of the equation can cause changes in the condition number of A times as large in the solution. Now, what does the condition number tell us? The condition number is a good indicator of how close is a matrix to be singular. The larger the condition number, the closer we are to singularity. It is also very useful in assessing the accuracy of solutions to linear systems. In practice, we don't really calculate the condition number. It is merely estimated to perhaps within an order of magnitude. Okay, let's have the given example. So suppose we have this matrix A, and then this is our given vector. Our matrix A is being multiplied to our vector x, and then C is our solution vector. Now, let's try to see and make changes in our given matrix or solution vector. Now, the question is the given problem an ill-conditioned? Is the given condition number is ill-conditioned or well-conditioned? Okay, let's find out. Now, in this case, if we will make small changes in the element of our matrix A, will it result to a small change also in our solution vector C? If that would be the case, then that is a well-conditioned problem. Now, how do you know that it's a well-conditioned? What is our basis? We will find out later on. Now, on the other hand, if we will make a small change in any of the element in our matrix A, and then it has a large impact or large change, it results to a large change in our solution vector C, then our problem is said to be ill-conditioned. Okay? Now, let's try to dig deeper in this particular slide. Now, in this case, large condition number is bad. Okay? So, we have to find out the basis for saying bad and not bad. Okay, how do we know that it's just a small change? Okay, sige. Now, let's understand the ill-conditioned problem and the well-conditioned problem. Now, if we talk about well-conditioned problem, small changes in the data produce small changes in the solution. Again, if you create a small change in any of the matrix, in any element of your matrix A, say for example, then there's also a change in the solution vector, but it's just a small change, then that is still considered as well-conditioned problem. And again, you have to see this, the statement also as your basis for you to decide if it's a well-conditioned problem. And it will be shown in the next line. Okay? On the other hand, if we talk about ill-conditioned problem, small changes in the data produce large changes in the solution. Even if you just add 1 to a specific element in a matrix, say for example, the original element is 1 and you made it 2, and then it really affected the solution vector largely. In that case, we can consider that one as ill-conditioned problem. Small changes in a specific matrix or vector, but then again, it has a large impact on the other. Okay? So, how to know if it's large or a small change? Okay? Now, let's have the given statement. And this is read as condition number of matrix A is equal to, okay, that's it. Condition number of matrix A, denoted as cond A. Okay? That's how you read this one. I'm sorry for the mistake earlier. Now, let's try to see the statements. Okay, if the condition of the number of matrix A, if the condition number of matrix A is approximately equal to 1, then it is well conditioned. You have to remember that part. On the other hand, if the condition number of matrix A is greater than 1, then it is ill conditioned. And that is why you should have small change. It should be approximately equal to 1 so that it will be called as well conditioned. Okay? Anyway, we will try to find out if a given problem is ill conditioned or well conditioned in our examples. Okay, let's talk about some examples illustrating the condition number of a matrix. Okay? In this particular part of the lesson, we will just identify the condition number given the formula, which was presented earlier. And then we will also find out if the given problem is an ill-conditioned or a well-conditioned problem. Okay, let's start. Now, for our first example, okay, consider the given. So, notice here that the process will not be shown. You can actually make use of mathematical software to input the following data so that the value of x sub 1 and x sub 2 will be computed. So we will skip the solution part and then let's go directly to the result. Okay? So given the matrix which has elements 400, negative 800, negative 201, 401, and then a vector. And of course, our vector here is unknown. We have to find out the elements of our vector. And the solution vector is 200. Elements is 200 and negative 200. So if we will use mathematical software, you will get the value of x sub 1 as negative 100 and x sub 2 is negative 200. Okay? Now, what if we will make a change in the matrix A? Okay? This is still a matrix A as presented earlier. And let's make a small change. Okay? So, let's rewrite the given matrix and let's change 400. Let's add 1 to make it 401, and it's highlighted here in this part. Let me use laser point. Okay, now in this particular problem, let's see if it will affect our vector. Okay, solution vector. Let's have this. Okay, now as you can see, even if it's just a small change, it affects the solution vector largely. So x sub 1 this time is 40,000, and x sub 2 is 79,800. And therefore, since there's a large change, it's considered a seal condition problem. Okay? Let's consider this example, and this time around, we are going to use this formula. Condition number of matrix A is equal to the norm of A infinity to be multiplied to the norm of A inverse infinity. And as you can see here, we are using the infinity as our subscript. Okay? Now, let's find out what is a matrix norm. So, we have to give a brief definition of matrix norm since we are going to use this one in solving the condition number. So, let's use a very simple example. These are the values of matrix A. So, we have the following elements, 1, 0, 2, 1. Now, this time, let's try to solve the norm of A. Okay? The norm of A. So, how do you do that? All you have to do is to get the largest row sum of the given system. Now, we only have two rows here, this row and this row. So, let's try to identify the largest row sum. And by inspection, if you will get the absolute value of 1 and 2, and add the 2, that will result to 3. Okay? So, this is actually the norm of A infinity. Okay? It's basically 3. Simple as that. Now, this time, let's talk about finding the A inverse, the norm of A inverse infinity. Now, if this is our original matrix, A, B, C, D, you have to take note of the given diagonal. You just have to interchange A and D, and then you have to make B and C negative. Okay? So, how are you going to do that? Now, you also have to consider the determinant of matrix A. So, for you to solve for the inverse, you have to get the determinant and follow the formula. Okay? So, in the next slide, I'll be showing you the same example. Now, this is an overview. Now, in the next slide, it's a complete example. Okay? Now, let's continue. Now, consider the given matrix having the problem, the elements 400, negative 801, negative 201, and 401. And then, let's try to get the determinant, okay, of matrix A. You know how to get the determinant? Multiply the 2 and subtract it to the product of these two. So, the determinant of A this time is negative 400. So, if it's negative 400, let's solve for the inverse of matrix A. Okay, the same process. I think it's just good to skip this part since this is not our focus. Okay, now you just have to process this one, and once you're done, you will get the following elements. Okay, now after processing everything, I want you now to identify your row sum. Okay, and try to add the following elements in a particular row, and it must be the largest sum. The sum must be the largest among the elements of a particular row. Okay? Now, let's talk about finding our norm of A infinity. Okay? The same thing earlier, we will just look into our original matrix. This is our original matrix A. And then, we will identify the row which will produce the largest sum. Okay? Always remember to get the absolute value and then add it. Add the two elements. Okay? So the absolute value of negative 801 is of course 801. Add it to 401. The result is 1201. And that is the value of our norm of A infinity. Okay? So this time, let's get the norm of A inverse infinity. So in this case, we will focus on our result. Okay? And by inspection, this is actually our row sum. Okay? So, get their absolute value. Get the absolute value of each element found in that particular row, and then add the 2, and that will result to 3. Now, this time, we can now go back to our formula. Okay, let's solve for the condition number. So, our condition number this time will be, okay, let's just substitute our condition. Our norm of A infinity is 1201, and our norm of A inverse infinity is 3. The condition number is basically 3603. And take note, 3603 is obviously, it's greater than 1. So if it's greater than 1, this problem is considered as an ill-conditioned problem. Okay, it has a really large effect. Okay? Okay. Now, let's try another example. Okay, now this time, I will not show the solving since in this particular example, mathematical software is being used. So, I just have to explain to you the condition number. Okay? Sige. Now, let's still use the given formula. This time, there's no infinity subscript. Okay, we are using the original formula. Now, in this case, try to observe. We have the norm of A, and that is 6, given this matrix, of course. And the norm of A infinity is 8. Okay? So, they also have their A inverse. So, in this particular part, if the subscript is 1, the A inverse is 4.5. The norm of A inverse is 4.5. And the norm of A inverse infinity is 3.5. So, by computation, we can see, of course, a very large result. So, in this case, we still have ill-conditioned problem. Okay? So, if ever in the future lesson, you will encounter a very small condition number, then you can say it's a well condition. Most especially is if it's approximately equal to 1. Okay? Now, let's have the next example. Now, a certain mathematical software is still used in solving the given value. But anyway, let's try to consider this system. Okay? This is our system. And try to check every element. Okay? And, of course, using the software, the value of x and y in this particular vector can be solved. Okay? And this time, let's have a small change in the coefficient matrix. Okay? So let's have a small change in the coefficient matrix. Now, this time, we have 4.1. Okay, just 0.1. And the rest of the values are the same. Okay? Sige. Now, using mathematical software, you can use anything. Okay. Now, check this slide. We are using MATLAB in computing the given problem. So, as you input the values there, we can see the result here. Okay, we have -10 and -20. Okay, take note of this one. And let's move on to the next part. Okay, now, as I mentioned earlier, we made a very small change in our first element of matrix A. So from 4.0, it became 4.1. Just 0.1. Okay, change. And then try to look at the result. It really affected the value largely. Okay, so it became 400 and 780. Now let's see our computed result here in the next slide. Okay, check this particular slide. Okay, now in our original system, okay, the value of x is -10 and the value of y is -20. After we created a small change in the coefficient matrix from 4 to 4.1, when we computed using the MATLAB, the value of x now is 400 and y is 780. So, this is still considered as an ill-conditioned problem. So, majority of the problem here really are ill-conditioned problems. Okay? Sige, there's a large change, hence the system is ill-conditioned. Okay, you have to remember that the condition number helps us to check whether the system is ill-conditioned or not. When the condition number becomes large, the system is regarded as being ill-conditioned. Okay, when the solution of the system Ax is equal to b is highly sensitive to the values of the coefficient matrix A, or the right-hand side of the constant vector, b, that is small change in one of the values of the coefficient matrix, or the right-hand side vector causes a large change in the solution vector, the system is said to be ill-conditioned. Okay? And that would be all. Thank you.